Let us now give a slightly more formal context for these operations that we were talking about. Let us define what is linear filtering and what are convolution and correlation. These are really important notions in this type of tasks that we were talking about so far. So let's get back to our neighborhood operations, and let's define what it means to when they're linear. So we are looking at a particular pixel, we are looking at a particular neighborhood, and we are performing operations on these pixel values in the particular neighborhood in order to produce a response in the output image in the particular place that corresponds to the central pixel of the neighborhood. And we were looking at a number of ways to look at the pixels in the particular neighborhood, and one of these was weighted average, weighted mean, where we were defining filters with particular coefficients, which we called weights. And the operation that we were performing then was to multiply each of the pixel values in the neighborhood with the corresponding weights in the filter, in the mask, and then sum up all, and in that way produce the output value. So the operations that we were performing in a number of situations were to multiply the values in the neighborhood with the corresponding weights and to sum. Actually, this set of operations is what we call linear operations. Linear operation is defined as an operation that fulfills the following criterion here. So if applied of a scaled sum, it performs as the sum of scaled operation values on the individual input variables. So this is what a linear operation fulfills. And whenever we are performing operations which combine multiplication with a constant and subsequent summation, then we are talking about linear operations. And they have a number of nice properties. They are very popular to use, therefore. And that is also the reason why we are particularly now interested in that type of neighborhood operations, which is expressed as a combination of multiplications with a constant and subsequent summation of the pixel values. If we know what we are going to do, and that is to multiply the pixels in a neighborhood with constants defined by a filter and then sum them all, then we do not really need to think a bit about much more than positions in the filter mask and values that are assigned to it, to each of these positions. So the operations are then defined if we are talking about linear filtering. These positions in the filtering mask are defined with respect to the central pixel of the filter. That one is then assigned position 0, 0. That one corresponds to the central pixel of our neighborhood, while the rest of the positions in the filter are then defined or described by the locations, the coordinates, with respect to that central pixel. So the left upper corner is at the position -1, -1, which means that it is one row and one column before the central pixel, and so on. So we can then describe or have these coordinates on mind when we are talking about transversing the values that are given in our filter these weights, these constants that are actually defining our linear filtering. Once when we know these weights, then we are essentially talking, we can say that we are talking about linear combination of the values in the neighborhood of a central pixel that we are looking at, since linear combination would be this multiplication by a scalar and subsequent summation, and the scalars are defined for each position with the filter mask. We can also talk about scalar product if we say that this is these values here can be arranged and seen as a vector, and these as well. Then we have corresponding multiplications and subsequent summation to produce the output value in the filtered image. So this, what we describe now, is what we also used already in a number of filters, but not all, in the previous part on smoothing and edge detection. Linear neighborhood operations can be realized by convolution and correlation. Now we are actually giving names to the processes that we were performing so far. Let's see what we were doing so far. Let's start with what is correlation. It says, translate the filter over the image. Okay, that's what we were doing. For each position, compute linear combination of the image values using the coefficients defined by the filter mask. Linear combination would then include multiplication with a scalar defined by the mask and subsequent summation, assigned as output at the corresponding position. So that is exactly what we were doing so far. Okay, so we can say that all our filtering so far was done by correlation. What is then convolution? Translate the mirrored filter, and mirrored then in this case is in both X and Y directions. So flipping in X and flipping in Y, or we can say rotating by 180 degrees. So change the filter essentially, and then what? Translate it over the image, and for each position, compute linear combination of the image values using the coefficient defined by the mirrored filter mask, assign as output at the corresponding position. So whatever comes after is essentially the same as what we did before and what is done by correlation. So the only difference between correlation and convolution when it comes to how to compute them is what we do with the filter. Either we use the filter as given, or we, before applying it, we actually mirror it in X and Y direction. So considering that for symmetric filters, it will not, we will not, their mirrored versions will be exactly the same as their original versions. We may say that we were also, in a number of cases, performing convolution. So, for example, when we were doing when we were computing mean or even Gaussian, we wouldn't notice that if the filter was mirrored before application or not. So in these cases, we were performing both correlation and convolution. So in essence, there is not much of a difference between these operations. So why do we need both? Or why do we talk about both? Let's say what actually happens if the filter is not symmetric. So if there is really different filter ones when we mirror it. Let's look at a 1D signal for simplicity. So this is a discrete signal which has only one value, which is non-zero, and that is value 1 here at one position. So this is a discrete impulse. And let's look at a very simple small filter, which is described here, and let's apply correlation. So we are sliding this filter over this signal, and we are computing linear filter. So we are computing a weighted sum over this signal by this filter, and the response is actually as we see. So this is the correlation. It is somewhat shorter, or like shortened by 2 because of fitting this filter only fully where it can fit, and the rest is just ignored. But what we notice here is that we actually have a mirrored copy of the initial filter at the location of the impulse. So that is what we get. We didn't mirror the filter before applying correlation, but what happens is that an impulse will detect and flip, or and will mirror the filter, or will resonate in that way, in that sense with the filter. So let's see what happens if we do the same by a convolution. So we use the same signal, we use the same filter. In order to apply convolution, we will then first mirror the filter. So in this case, it will be only in one direction, because this is 1D filter. We will perform the same operation by this mirrored filter. That will be then convolution of this signal by this filter. This means that we will multiply the values of the signal by the values, the constant given by the filter, and sum at each position. And then we see that we will have a response that is actually equal to the filter. So the filter is repeated at the particular position of the discrete impulse. So this is what is the difference in application of correlation and convolution with the same filter on the same signal. Now, when we expressed what convolution and correlation are in words, and then also show the small example, we can formalize that and give their definitions. Both correlation and convolution are defined for continuous functions, and then they are computed by integration instead of summation, and these integrals go over the whole function domain. But in the discrete case, for discrete 2D functions, so what is relevant for our images, definitions of correlation and convolution look as follows. So the output in both cases, named G, by correlation of a function f by, we can say, a function h, or a kernel or a filter h, is computed as the sum of products of function values and kernel or filter values, where the coordinates of the kernel are actually those that we defined as relative positions in the filter with respect to the central pixel, so those -1, and so on. And this summation is defined over the values that, over the coordinates or the positions that are defined by the kernel. So essentially, the summation goes over the neighborhood that we are observing. In case of convolution, we have a different symbol, and we have this mirroring of the filter incorporated in the definition. Mirroring of the filter or mirroring of the function actually have no difference, so both of these definitions hold, and this minus here or here, as opposed to this plus here, actually reflects this operation of mirroring, of rotating by 180 degrees of the filter before its application. Otherwise, both of these definitions are very similar. We will stay now a bit more on convolution. So this h, this here, which we use to apply to our image function, is the function itself. It is often referred to as impulse response function. So we can recall the example that we had, a small example in 1D case, where our discrete impulse signal actually reflected the filter, the function h, and therefore the name. Point spread function, we will come to that soon and explain what this actually means. Convolution kernel. So finally, we were using this term kernel or mask. Now we are adding this convolution kernel or convolution mask as well. Finally, when we have this connection with the actual operation of convolution. So these are different names that can be used interchangeably for defining this particular function h, which we use to act on a given function f. However, we see that there is really symmetry in this definition, and the roles of h and f can be exchanged, which is an important property of convolution. Some more properties of convolution. So convolution is linear, and that is its important property. It is scaling invariant. That means that convolution essentially, let's say, commutes with multiplication by a scalar. We will have the same result if we take when convolving the function with some convolutional kernel, we can take a multiple of the function and then perform convolution by kernel. We can equally well first convolve and then multiply with the scalar afterwards, or we can take the scalar and apply and multiply with the kernel before applying convolution. The result will stay the same. Convolution is also distributive with respect to summation, and then that means that we can convolve a function with the sum of kernels or convolve with each of the summands and sum afterwards without changing the result. Important property of convolution is that it is translation invariant, that its result is not affected by the position where it is applied, and the translates the translation will not change the value of convolution. So translating result of convolution of two functions will have the same effect as translating one of the or the other of the functions before performing the convolution. Convolution is commutative, and that is what enables this statement that the functions, what is a function and what is the, let's say, the image or the kernel is maybe more kind of evident, but in a more general case, the rows of these two functions, f and h, can be exchanged. And also very important property is that it is associative. And that means that the order of grouping of convolutions can change, we can perform sequence by grouping without exchanging, without changing the order in any groups which seem suitable. Just to note, these list of properties, especially commutativity and associativity, are really important properties of convolution and are not shared by correlation. So correlation, even though it is very similar to convolution in terms of how it is computed, does not share the same nice properties. For example, it is not associative and is not commutative. And that is quite important. This is quite important when further developing theory, filtering theory, and actually focusing on convolution as operation, which is involved in filtering and definitions, how linear filtering is performed. Linear filtering is then actually realized by convolution. So formal way to express any linear filtering is by using convolution. Any linear filter can be expressed by convolution, and any convolution can perform linear filtering. So what is linear? As a reminder, this is any filtering that involves computing scalar product, which involves multiplication by a scalar by weights and summing the values that are contained under the mask. Now, if we talk about, if we exploit a bit the nice properties of convolution, we can make linear filtering in higher dimensions benefit from them and becoming maybe faster or easier to implement. Let's analyze a bit what can be done. So there is a nice property of some filters that is called separability. That means that some filters can be expressed, let's say, if they're, for example, 2D filters, small matrices, they can be expressed as a outer product of 1D vectors. And considering or adding to this a nice property of convolution, that it is associative, then we can say that if I want to convolve my function with a filter, let's say H, which happens to be separable and can be expressed as a product of two filters of a smaller, lower dimension. For example, this is a 2D image. I would apply 2D filter H, but I can actually express it as a product of two 1D filters. Then I can use associativity of convolution and say that I will first apply 1D filter on my image and then follow that by additional application of the other 1D filter on my image. Why is that good? Well, it appears that a number of operations performed in these two implementations of the same operation differ, and that it is faster and sometimes easier to implement this type of filtering where separability of the filter is used. So some examples of separable filters and what this decomposition actually means. Sobel filter that we discussed when we used as an approximation of Gaussian derivative. One of the masks was defined as this filter here. What we can decompose it to is this product. This is called outer product of these two vectors. So a vector times another vector transposed. And this matrix multiplication will actually result in this matrix, where we can even see that this here is some way of smoothing the image, while this here really corresponds to what we discussed when we talked about how to have a simple mask for differentiation. So now we can even see that Sobel filter can be decomposed into its smoothing and differentiation component. It is not necessary to have interpretation of each of the components. It can be enough to really be able to mathematically decompose this 2D matrix into outer product of two vectors in order to use this property, but sometimes it really helps us to understand also what a particular filter actually does. Another example, very simple one, is this mean filtering, where we can realize this application of such a 2D filter, which computes average in a 3x3 neighborhood by this column of ones and this row of ones, so vector times transposed vector of ones with suitable constants, and we have actually decomposition of of this mean filter into two 1D filters. There are other filters which are separable. For example, Gaussian is separable, which is one more good property of Gaussian filtering. But there are others which are not. So, for example, Laplacian of Gaussian, that we also commented on, is not separable. And then sometimes it is quite like gains of having separable filters are such that there is also a desire to find approximations of important filters which are separable, even though the original filters are not separable. So since Laplacian of Gaussian is an important filter, but not separable, then there is a proposed and well-known and often used approximation, which is then realized as difference of Gaussians. So with selecting two suitable Gaussian filters and applying them sequentially or like jointly, we can approximate this log filter. However, this dog filter will then be separable, and we can use advantages of that. So how big are the advantages? Let's take a look at this example. So we have an original image. And what we are proposing now is to filter this image with 1D Gaussian, which then means that we are separating, decomposing our Gaussian filter in its two components, horizontal and vertical one. So here is the result of convolution with the horizontal component, followed by convolution of the vertical component. And due to the fact that these two, when multiplied, actually result in a, let's call it normal 2D Gaussian filter, this result is then the same as what we would get with ordinary 2D filtering. However, if we look at the number of operations that are used in both versions of this type of filtering, then we know that if we say that in this case we have quite big Gaussian, so 31 times 31 is the size of the kernel. Such a kernel in 2D has 31 squared values, and that is how many multiplications have to be made and summations. So in total, by direct filtering by Gaussian filter, 2D Gaussian filter of size 31 times 31, we perform 961 operations, multiplications and additions. If we decompose Gaussian filter, relying on its separability, then we have first filtering by 31 times 1, and that is the number of values and number of operations determined by that. And then we go one step further, but we again have now in this case 1 times 31 size of a filter, which means that we have only twice 31 operations to make in order to compute the same result, which is only 62 multiplications and additions involved. And that shows that for large filters, the difference in the number of operations performed can be big enough to actually justify our need, or desire rather, to work with separable filters and to use their separability. Similarly, relying on on the same property of convolution, and that is its associativity. We can think of performing sequence of filters, which is maybe even which is a step further from performing sequence which results from separability of filters. So we can simply perform a number of whichever filters and see what result can come out from it. So we can say that we are performing one filter and then continue with another filter and the third and so on. We can also say that the same result can be obtained by grouping all the filters that we have in the sequence and let's say producing one filter by convolving these filters first and generating the finally desired one which corresponds to the whole sequence. An example is shown here where we are performing subsequent filtering of this input image by, let's say, this is averaging in a square neighborhood. And then we have a filter which is performed, which looks like this, and then is performed further and further. We can actually do two things here. We can subsequently perform this same averaging filter to every subsequent image, or we can perform these resulting filters to the first image. So if I perform this filter to this image, then I actually followed this model. If I use a sequence of filtering by this square, then, or averaging within this square neighborhood, then I am following this sequence. Interestingly, this also gives me some way of, let's say, approximating or approximating more complex filters by a sequence of simpler ones. And in this particular case, we actually see that subsequent application of averaging filter will eventually come closer and closer to a Gaussian kernel, and a way of performing Gaussian smoothing can then actually be that we instead perform a sequence of averaging filters, and the longer the sequence, the closer to a real Gaussian we can come. In this case as well, just to emphasize one more time, we rely on the property of convolution, which is known as associativity, which allows us to group several filters and produce one final filter to apply to the image, or to essentially apply sequence of filters and get to the same result. Now we talked a bit more about convolution, and we will continue and conclude in this last part of the lecture with getting a bit more of correlation, also opening a new application of filtering, where it is not only for enhancing the particular low-level details such as edges or removing noise, but as said, we can come a bit closer to maybe detecting objects of interest in our images and come to object detection and segmentation by still using operations that we know and relying on filtering.